So the next point is variation of molar conductance and specific conductance with the dilution. How this molar conductance and specific conductance, they will vary with the dilution. What is dilution here? Addition of solvent or water is called as what? Dilution. If you add water or solvent to the electrolytic solution, that process is called as what? Dilution. Simply the addition of water is dilution here. If you add water, what happens to the electrolytic solution? Concentration of electrolytic solution decreases here. Here dilution and concentration both are what? Inversely proportional to each other. Dilution increases, addition of water is more and more, then what happens? Concentration of the solution decreases. These two are inversely proportional to each other. Now we will see with the dilution how this molar conductance and specific conductance varies. What is dilution? Addition of water to the electrolytic solution. So what is the effect of addition of water to the electrolytic solution? We will see it now. The formula for the molar conductance is what? Molar conductance is equal to specific conductance divided by concentration. So if you rearrange this one, it can be written as concentration is equal to specific conductance divided by molar conductance. Already we know that for dilution, what happens? Concentration decreases. These two are inversely proportional to each other. As the dilution increases, if you add more and more water, what happens here? Concentration will decrease. If the concentration decreases, specific conductance decreases because these two are directly proportional to each other. Next, if concentration decreases, molar conductance will increase here because these two are inversely proportional to each other. Now we will see why this specific conductance decreases with decrease in the concentration. Suppose if you add water to an electrolytic solution, now what happens? Here in an electrolytic solution, cations and anions, these are present here. If you add water, what happens here? They will move far away from each other because they will get more and more space and they will move far away from each other. Then as they move far away from each other, the number of ions per unit volume of the electrolytic solution decreases. Here specific conductance decreases with increase in the dilution because K depends on the number of ions per unit volume. What is specific conductance here? Specific conductance is, that is the conductance due to all the ions that are present in 1 unit volume. Here in 1 unit volume, number of ions changes, here specific conductance changes. If number of ions per unit volume decreases, specific conductance decreases here. Now if you add more and more water, these ions, they will move far away from each other, so that the number of ions per unit volume will decrease. As a result, here specific conductance will decrease here. So specific conductance decreases with increase in the dilution because K value, that is specific conductance, depends on number of ions per unit volume. With increase in dilution, number of ions per unit volume decreases, hence here specific conductance decreases. Now we know that molar conductance increases with increase in the dilution because dilution increases, concentration decreases and molar conductance will increase here. Next, another point is maximum conductance, that is maximum electrolytic conductance is achieved only when added electrolyte undergo complete ionization, because whenever it undergo complete ionization, more number of ions will be formed, so that conductance will increase. With increase in the number of ions, conductance, that is molar conductance, will increase here. Another thing is, once they are ionized, these cations and anions in the concentrated solution, they are very close to each other. Since they are very close to each other, there is a force of attraction between these two. Due to force of attraction that is present between these two, they cannot move independently and very fastly because of this force of attraction. Whenever you add water here, if water is added, these ions, they will move far away from each other, and then the force of attraction between the cation and anion, that will break here. Once the force of attraction between cation and anion, that is interionic force, that is broken, then they start moving independently. Then again what happens? Ionic conductance will increase here. That's why maximum conductance is achieved when electrolyte is completely ionized, because more number of ions are formed here, and interionic forces between cation and anion are broken. Once complete ionization takes place, that conductance will not increase 100% because again there is a force of attraction between what? Cation and anion. Because of this force of attraction, they cannot move very fastly. So in order to break this force of attraction, what you are doing here? You are doing dilution. Dilution is nothing but addition of water. Once water is added, they will move far away from each other and the force of attraction between the ions is broken. Then they move independently and very fastly. Again, there is an increase in the conductance. So, the maximum conductance is achieved only when added electrolyte undergo complete ionization and the interionic forces between the cation and anion are broken here. Okay, next point. So, the next point is variation of molar conductance for the strong electrolyte. Already we know that the maximum conductance will be achieved only when the electrolyte undergo complete ionization and whenever the force of attraction between cation and anions are broken, then they start moving independently. Again, their conductivity will increase here. So, there are two factors to achieve maximum conductance, that is the added electrolyte must undergo complete ionization, and the second thing is you have to break the force of attraction between the cation and anion. Then they start moving fastly, again their conductivity increases. But in case of strong electrolytes, already they will undergo what? Complete ionization, so that all the ions will be formed. So, in case of strong electrolyte, just you have to break the force of attraction between the cations and anions with the dilution. If you add water, these cations and anions, they will move far away from each other. As a result, their interionic forces will decrease and they start moving fastly. Hence, their molar conductivity will increase slowly. Then it reaches a maximum value at particular dilution. That dilution is called as what? Infinite dilution. So, in case of strong electrolytes, they are undergoing complete ionization. In the concentrated solution, they are close to each other. Hence, there exists a interionic force between them. As a result, their conducting ability is very less because they cannot move independently. If you add water, these cations and anions, they will move far away from each other. As a result, their interionic forces will decrease and hence their molar conductivity will increase slowly. And it reaches the maximum value at particular dilution. That dilution is called as what? Infinite dilution. If you go on adding more and more amount of water, their conductivity will slowly increase and it reaches a maximum value at particular dilution. The dilution at which this molar conductivity it reaches a maximum value, that is infinite dilution we call it as. So, the molar conductance of an electrolyte at infinite dilution is called as what? Limiting molar conductance. This is the maximum value of molar conductance. After this, if you add more and more amount of water, there is no increase in the molar conductivity. That value of molar conductance is called as what? Limiting molar conductance. So, for strong electrolyte, limiting molar conductance is achieved with a very small amount of solvent only. Already they are undergoing complete ionization. Just you have to break the force of attraction between cation and anion so that they will start moving fastly here. So, for strong electrolyte, you keep in mind, just you have to break the force of attraction between them so that they start moving fastly and again their conductivity will increase. Their ability to conduct increases and it reaches maximum value here. So, this is about strong electrolyte. So, the next point is variation of molar conductance for the weak electrolyte. How the molar conductance of weak electrolyte changes with the dilution. So, one thing we know that molar conductance increases with increase in the number of ions in the solution, and another thing is with the decrease in the force of attraction between the ions, again molar conductance increases. So, already we have discussed for strong electrolyte. For strong electrolyte which undergo complete ionization, 100% ions will be formed. So, whenever 100% ions will be formed, here cations and anions in the concentrated solution, they are very close to each other. So, what happens here? There exists a force of attraction between them. Because of this, these cations and anions, they cannot move independently and fastly. So, in order to break this force of attraction, what you are doing is you are adding some amount of water. That is nothing but dilution we call it as. On adding water, what happens? These cations and anions, they will move far away from each other so that the force of attraction between them breaks and they move independently and very fastly. As a result, their molar conductance increases. This happens in case of strong electrolyte. But in case of weak electrolyte which undergo partial ionization with the increase in the dilution, increase in dilution is nothing but you are adding water. If you add water to the weak electrolytic solution, degree of dissociation of weak electrolyte increases. Initially it is undergoing partial ionization. If you add more amount of water, it undergo what? Complete ionization, that is degree of dissociation of weak electrolyte increases. As its degree of dissociation of weak electrolyte increases, total number of ions in the solution that contains 1 mole of electrolyte increases. That is, the number of ions increases. As the number of ion increases, their molar conductivity suddenly it will increase here. Always you keep in mind, increase in the molar conductance due to increase in the number of ions is more than the increase in the molar conductance due to decrease in the force of attraction. That's why in case of weak electrolyte, always you keep in mind their molar conductivity suddenly increases with increase in the dilution. So here another relation, that is the relation between molar conductance and limiting molar conductance. So what is limiting molar conductance? Already I have discussed. It is the maximum value of molar conductance at particular dilution. That is called as what? Limiting molar conductance. After reaching this maximum value, if you add further water, there is no increase in the value of molar conductivity. That is called as what? Limiting molar conductance. Already we have discussed this one. So the relation between the molar conductance and limiting molar conductance is molar conductance is equal to limiting molar conductance minus A into square root of C here. Here this is molar conductance, limiting molar conductance. A is constant for a particular solvent and C is nothing but concentration of the solution. So one thing, the limiting molar conductance is nothing but the maximum value of conductance that is achieved only when added electrolyte undergo complete ionization, and when the force of attraction between the cation and anion are broken, then you will get maximum value of molar conductance. So the next point is relation between molar conductance and limiting molar conductance. Already we know this equation, molar conductance equal to limiting molar conductance minus A into square root of C here. And this equation, it is in the form of Y is equal to mx plus C, and this molar conductance is taken along Y axis and concentration is taken along what? X axis. This M will give what? A negative slope, and here this will be your Y intercept. Limiting molar conductivity, this will be Y intercept. If you take the graph of molar conductance versus concentration for strong electrolyte, the graph will be a straight line. And for weak electrolyte, the graph of molar conductance versus concentration, it will be not a straight line. Only for strong electrolyte you will get a straight line, but for weak electrolyte this graph will not be a straight line. And here for strong electrolyte, the limiting molar conductivity can be calculated just by extending this line to the zero concentration. If you extend this line to the zero concentration, it will touch Y axis at this point, so that this Y axis, this Y intercept, it will give limiting molar conductivity of strong electrolyte here. So for strong electrolyte, experimentally its limiting molar conductivity can be calculated in the laboratory. But for weak electrolyte, the graph is not a straight line. Since it is not a straight line, this line cannot be extended to reach zero concentration. If you extend this line, it will never touch zero concentration. So here you will not get any intercept in case of weak electrolyte. Therefore, the limiting molar conductivity of weak electrolyte cannot be calculated experimentally in the laboratory. Only for strong electrolyte we can calculate limiting molar conductivity. So here for strong electrolyte, the graph will be what? Straight line. For weak electrolyte, this graph will not be a straight line. Limiting molar conductivity of strong electrolyte can be experimentally calculated, but for weak electrolyte it cannot be experimentally calculated. So the limiting molar conductivity of this weak electrolyte can be calculated by using a law, that is KOHLRAUSCH law of independent migration. According to this law, what happens? At the infinite dilution, if you add more and more amount of water at infinite dilution, electrolyte undergo complete ionization. That 100% ionization takes place, all the ions will be formed. And again, if you add more amount of water at infinite dilution, the force of attraction between cation and anion will be completely vanished. So that at infinite dilution, these cations and anions, they will move independently and they will contribute towards the total molar conductivity. So here KOHLRAUSCH law says that according to this law, the limiting molar conductivity, or you can say the molar conductivity of an electrolyte at infinite dilution is compulsory here. The limiting molar conductivity of an electrolyte at infinite dilution is the sum of individual contribution of cation and anion here. So that here the total limiting molar conductivity of electrolyte is, it is the sum of limiting molar conductance of cation plus limiting molar conductance of anion it is. In general, if I take an electrolyte, that is AX and BY, general formula, so that it will form X times of cation A and Y times of B anions here. So for this one, the limiting molar conductivity is X times of limiting molar conductivity of cation, Y times of limiting molar conductivity of anion here. For example, again if you take NaCl, for this one the limiting molar conductivity of NaCl will be equal to limiting molar conductance due to Na plus ion and limiting molar conductance due to Cl minus ion here. And again if you take AB2 type of electrolyte, that is limiting molar conductance of MgCl2. In this one the limiting molar conductance will be equal to what? That is limiting molar conductance of Mg plus 2 ion and 2 times of limiting molar conductance of Cl minus ion it is. So now we will discuss applications of KOHLRAUSCH law here. Already we know that for weak electrolyte limiting molar conductivity cannot be calculated in the laboratory, that is experimentally we cannot calculate limiting molar conductivity of weak electrolyte. But the limiting molar conductivity of weak electrolyte can be calculated by using what? KOHLRAUSCH law here. So we know that if I take this CH3COOH, this is your weak electrolyte. For this one experimentally it is not possible to calculate its limiting molar conductivity. But if I take strong electrolyte like CH3COONA, HCl and NaCl, for these strong electrolytes we can calculate limiting molar conductivity. By using the values of limiting molar conductivity of these strong electrolyte, we can calculate the limiting molar conductivity of this weak electrolyte by using KOHLRAUSCH law here. So what I will take here, limiting molar conductivity of CH3COOH, this will be is equal to limiting molar conductivity of CH3COONA plus limiting molar conductivity of HCl here. In this one what I want? CH3COOH I want. Here CH3CO is there and here H is there. So here you have to remove Na and here you have to remove what? Cl. That's why minus limiting molar conductivity of NaCl. So this is the formula to calculate limiting molar conductivity of this CH3COOH. Similarly, here this barium sulfate, again it is what? A weak electrolyte for which that limiting molar conductivity cannot be calculated experimentally. But if I take a strong electrolyte like barium chloride, H2SO4 and HCl, for these strong electrolytes we can calculate that limiting molar conductivity. The trick for this one is, in these three formula you have to take only barium and sulfate. From these two you have to take what? Here barium is there and here sulfate is there. So these two you have to add, and what is left here? Cl and H. These two must be removed, so that limiting molar conductivity of HCl must be subtracted here. So the limiting molar conductivity of barium sulfate is equal to limiting molar conductivity of barium chloride. In this one you will get barium plus limiting molar conductivity of H2SO4. In this one you will get SO4. So you got these two here. Now what is extra here? That is hydrogen and chlorine. These two must be removed here. So minus 2 times of limiting molar conductivity of HCl, because here 2 times of chlorine is there and 2 times of hydrogen is there. So the limiting molar conductivity of barium sulfate is equal to limiting molar conductivity of barium chloride plus H2SO4 minus 2 times of limiting molar conductivity of HCl here. Similarly, this HF is a weak electrolyte which cannot be calculated. So the limiting molar conductivity of HF is what? Just you have to take HCl, NaF and NaCl. In this one you will get H, limiting molar conductivity of H plus ion. In this one you will get what? Limiting molar conductivity of F minus ion. So these two you have to add. Next, what you have to remove here? Na and Cl you don't want. Here only HF is required. So here you have to subtract what? Limiting molar conductivity of NaCl. So the limiting molar conductivity of HF will be is equal to limiting molar conductivity of HCl plus limiting molar conductivity of NaF. If you add these two, you will get H plus ion and F minus ion. So the limiting molar conductivity due to H plus and F minus you will get. What you have to subtract here? Na plus and Cl minus. That's why minus limiting molar conductivity of NaCl you have to take here. So the next application of this KOHLRAUSCH law is identification of degree of dissociation, that is alpha value. Alpha value is calculated by using this formula. Alpha is equal to molar conductivity divided by limiting molar conductivity, or else if you are using equivalent conductance, alpha will be is equal to equivalent conductance divided by limiting equivalent conductance here. So again, by using this KOHLRAUSCH law, since you can calculate alpha value, by using this alpha value you can calculate what? That is dissociation constant for weak acid, that is K for the weak acid can be calculated. That is K is equal to C alpha square divided by 1 minus alpha. In this one, if you substitute alpha value, alpha is equal to what? Lambda m divided by lambda m naught. That is nothing but molar conductivity divided by limiting molar conductivity. If you substitute alpha value, this value here, you will get this one. On simplification, you will get this formula. This is concentration into molar conductivity square divided by limiting molar conductance minus molar conductance whole bracket, you will get into limiting molar conductance here. So this is what application of Kohlrausch's law. Still 2 more are there. So the next application is calculation of ionic mobility. Ionic mobility is nothing but movement of ions. This ionic mobility is perfect only at the infinite dilution, because at infinite dilution electrolyte undergo complete dissociation and you are adding more amount of water. These cations and anions, they are moving far away from each other, so that the force of attraction between them is broken. They will move independently. So only at infinite dilution ionic mobility will be perfect. So what we will take is limiting molar conductance. What is limiting molar conductance? The conductance at infinite dilution. So here what we are taking, limiting molar conductance is directly proportional to ionic mobility. Limiting molar conductance of cation is directly proportional to ionic mobility of cation. If you remove this proportionality sign, what you will get here? Again Faraday. So here limiting molar conductivity of cation is equal to Faraday into ionic mobility of cation. So ionic mobility of cation is equal to what? Limiting molar conductivity of cation divided by Faraday. Similarly here, limiting molar conductivity of anion is directly proportional to its ionic mobility, and here if you remove proportionality sign, again you will get a Faraday here. So ionic mobility of anion will be is equal to limiting molar conductivity of anion divided by Faraday. 1 Faraday already we know this one, 96,500 Coulomb here. Next one is identification of solubility. You can identify the solubility of electrolyte in the solution by using this limiting molar conductance, because here at infinite dilution, always you concentrate this term. At infinite dilution, what happens? Complete dissociation and force of attraction between cation and anion will be broken here. At infinite dilution, molar conductivity will be converted into what? Limiting molar conductivity, means further there is no increase in the conductivity value here. So at infinite dilution, molar conductivity changes to limiting molar conductivity, so that here at normal dilution we take it as concentration. At infinite dilution, concentration is directly taken as solubility, because here whenever any electrolyte is added to the water, first it undergo solubility. It undergo what? Solubility means it will be dissolved in the water. How much amount of electrolyte is dissolved in the water? Only that much amount will be ionized. So here at infinite dilution 100% ionization takes place, means it is 100% soluble here. So it is 100% soluble means concentration can be directly taken as what? Solubility. So for molar conductivity, the formula is concentration you will take. If you take limiting molar conductivity, this concentration can be replaced with the solubility. So here solubility is equal to, if you rearrange this one, solubility is equal to K into 1000 divided by limiting molar conductivity. So by using this limiting molar conductivity, we can calculate the solubility of electrolyte also. And these are the important applications of Kohlrausch's law.